In this video, we'll move into section 2.6, where we will discuss what we call implicit differentiation. There's no new differentiation techniques. There's no new shortcuts that we have to learn. We still have all the basics. You go back to 2.3, basic shortcuts, how we want addition, subtraction between terms, the power rule, the KX rule, all the little rewrites, the product and quotient rule for when we need them. We have our trig functions in 2.4, our chain rule in 2.5. But now, again, not a new differentiation technique, a little bit more understanding in the notation itself and expanding our knowledge. Because what we have had so far, every equation that we have dealt with has really gone with a function. So instead of writing f of x equals whatever, let me write y equals, and let's keep this one simple. Let's just keep it y equals x cubed plus 2. This is a function, so when we've taken a derivative, we've just kind of jumped in, the derivative of y is y prime, and then over here, the derivative is 3x squared plus 0. But one thing I want to point out is that what we have been doing the entire time, technically we are taking the derivative of the entire equation. And what we have been doing is specifically taking the derivative with respect to variable x. So over here we never noticed anything. If it was f, the derivative was f prime. If it was g, the derivative was g prime. But now let's formally use that Leibniz notation. Technically, we're taking the derivative on this side, and we're still using our regular shortcuts. If this was a 1x, the derivative would be 1, while a 1y, the derivative is 1. But now here's the extra bit. The fact that we're taking a derivative of a variable y with respect to x, this can be marked dy over dx. That's the indicator that you took a derivative of a variable with respect to a different variable. So we've never paid attention to that. We've just always take the derivative, we jump to this side, and on this side was just notation. So y prime, f prime, g prime. Here we're really seeing we are technically taking the derivative, but now we're embracing the notation. And the fact that we're taking a derivative of a variable with respect to a different variable, that's where we should really start to embrace the Leibniz notation. And instead of just leaving it y prime, be more clear, dy over dx, the derivative of y with respect to x. On the other side, technically, we can mark all variables. But over here, you took a derivative of a variable x, so it would get marked with a dx. And even though this is notation, there's a lot of situations where we get away treating this like a fraction. And that's exactly what we do here. Dx over dx. Well, if that was a number or a variable, x over x or 10 over 10, we would just cancel that, 3x squared times 1, so just 3x squared. And even same thing here. The derivative of 2 is 0, and then any extra 0 times anything is still just 0. So pointing out, technically, we've been applying implicit differentiation to all derivatives we have been taking. But now we need to understand when that is absolutely necessary. And it comes back to this. This is a function. You can isolate the y to use the function notation. If we look at the graph of this, it would pass the vertical line test. So again, it represents a function. But what if we want to talk about the slope of a tangent line of something that's not a function? If we're looking at a circle, and let me even put an xy axis through here. So a circle centered at the origin, and let's even make this 1, 2, 3, 1, 2, 3. So even more specifically, a circle centered at the origin of radius 3. This would have equation x squared plus y squared equals r squared. R is 3, so we would get x squared plus y squared equals 9. This is not a function, but we could still certainly ask questions like, what is the slope of the tangent line here? What is the slope of the tangent line here? There are tangent lines to this curve, so we could still think about the slope of the tangent line, and that still connects with the idea of the derivative. So here we're looking at a graph, and it's common equation form. You could say, well, I'll just solve this for y the same way you do here. Well, you subtract the x squared, but then you take a square root, and now you need a plus or minus. So it looks like you solve for y, but that's still not enough to make this a function, because you have the plus or minus here. You plug in a value for x, and you're getting two values for y. You plug in 0 for x, you get y as plus or minus 3, two y's to go with that one x value. So even if you just solve for y, that doesn't help. And let's go back to this one. Let's pretend it was y squared equals x cubed plus 2. Now we're in a similar situation. So basically the first thing I have to point out here is that anytime we're not dealing with a function, now we can't have directions, just find the derivative. We need more clarity than that. When it's a function, f of x is x cubed plus 2, find the derivative, that's very clear. There's only one variable here, we're taking the derivative with respect to that variable, and we get our traditional f prime of x is 3x squared, or your y prime 3x squared, whichever you prefer, depending on what you originally called the function. But now when you don't have a function, again, slope of the tangent line, questions about the tangent line, those are all still legitimate, and we'll still see the derivative gives a sense of instantaneous rate of change. But when we go to take the derivative, well, again, we need to be more clear. So if I gave you this is the original function, I'm sorry, not function, our original equation, I can't just say find the derivative. So now my notation would make that clear. That does say find the derivative, but it also makes it very, very clear, find the derivative of y with respect to x. So now we're kind of back on track. Most of these you will see, they are trying to get you to find the derivative with respect to x. That is our traditional approach. When we get to section 2.8, we'll see how we can apply this concept to word problems, and we'll start taking the derivative with respect to t for time. So we will get to that, but for right now, we need this extra notation. If I said find dx over dy, that is legitimate, but now I'll be taking the derivative with respect to y, not x. So let's do both of those. Okay, let's start finding dy dx. So taking the derivative with respect to x of the whole equation. So I'm still going left to right. I'm still everything we've ever talked about. Excuse me. Pardon me. Everything we've ever talked about as far as taking derivatives, observing the situation, what is the connection. This is all by itself. On the other side of the equation, just separated by addition. So we just get to go left to right. We don't need any rewrites. We don't have any product rule, quotient rule. This one is ready to go. So how do you actually take the derivative? It doesn't matter what the variable is. You still use your regular derivative techniques. Y squared, x cubed, both of these are the generic power rule. So power rule here, 2y to the first power. Or just 2y if you prefer. But here's the extra catch. You took the derivative of y and you did it correctly using your shortcuts, but now we need to mark that variable. And this is where I have seen even some textbooks avoid the Leibniz notation and just write 2y to the first power y prime. I'm not going to write that because can you already see 2y to the first power and then write y prime? The prime looks just like the exponent 1. So some people try and avoid writing the exponent so they don't have that confusion, but it's a really easy way to get confused. And again, it's easy to just say, because of the problems you see in the book, that we're always taking the derivative with respect to x, but that's not actually the case. That may be what we do in our homework, but it is legitimate to ask for dx over dy. So I strongly recommend don't just use a derivative notation, specifically use the Leibniz notation. There's the derivative of y with the extra indicator. That's the difference in implicit differentiation. So that's what I was saying at the beginning. It's not any new rules. It's just understanding derivatives can apply outside of functions, but if you're not looking at a function, that when you're looking at the equation, you need this extra notation, this extra marking. But now I keep going. Equals, and now the derivative on the other side, like we saw up here, 3x squared. I'm not going to do this anymore. I know some people, they like to just mark every variable and then go back and clean up the ones that were unnecessary. I think that's a bit of a bad habit. So I'd strongly recommend mark the variable that needs it, and a variable that doesn't, well, don't do anything extra. X cubed, 3x squared, nice, quick, easy derivative, nothing extra to worry about. And then, of course, plus 0. Here's the last catch, everybody. When you already start with a function, you take the derivative notation is already solved for. But in this case, you have to finish solving for your dy dx, right? We want the derivative, we want to find dy dx. There is a dy dx, but it's not automatically dy dx equals the way up here we had, well, we started with f, so the derivative began f prime equals. Now the dy dx just comes up somewhere inside the equation, and we have to finish by solving for dy dx. So algebraically, 2y times dy dx, I divided the 2y over, and that would be your answer, your dy dx for this equation. Still have a lot of little things to say, and then we certainly want to get a lot of practice. And just because this is implicit, we're still going to get all the other same practice. We'll still do some tangent lines. We have to talk about the higher level derivatives. So all good practice, not just getting our shortcuts, but all the reminders of what are derivative type questions, what are derivative situations. So we'll get to see all that. But very quickly, you want to point out, unfortunately now that this is not a function in the first place, its derivative also involves x's and y's. So unlike this notation, well, what's the slope of the tangent line when x equals 2? You have the derivative, you plug in x is 2, and that's it. X is enough for any question when we're dealing with a function, but when you have an equation, now you need x and you need y. So for instance, and actually let's just make this x cubed plus 4. This will make this next part a lot easier. You'll see in just a second. If I said to you, where does this have horizontal tangent lines, we'd still need our derivative, just like we always did, right? Where does this have horizontal tangent lines? You take the derivative, you'd set that equal to 0, and we get an answer x equals 0. We'd be done. Here, you'd still have to take the derivative, dy over dx. I'm going to come back to that in a moment. That's specifically the notation that goes with slope. These others will be derivatives, but they won't give us the slope of the tangent line. Slope is by definition rise over run, change in y over change in x. And this delta y and delta x, I'm cheating a little bit here. There's a little more notation to go with it, but that's essentially becoming dy over dx. So the idea of slope is how the y variable changes with respect to x, and that's exactly what we're getting here. So where does this have horizontal tangent lines? I need this specific derivative. I would still set it equal to 0. And here we get a quick lesson. A fraction equal to 0. You could cross multiply when it's this simple of a fraction, and 2y times 0 is just 0. But that does just boil down to setting the top equal to 0. I mean, just think about that with fractions for a moment. 0 divided by 5, 0 divided by -10, 0 divided by 27, that all just equals 0. So as long as there's no extra addition, subtraction, this type of basic fraction, you just set the numerator equal to 0. It looks like we get a clean answer. But again, x equals 0 is not enough. You would have to find the actual points here. So you'd have to go back, plug it into the original. This is why I made it a 4, so this works out a little nicer. We'd end up with y squared equals 0 cubed plus 4. So y squared equals 4. Y is plus or minus 2. So we'd end up with 0, 2 and 0, negative 2 would be the points where this has horizontal tangent lines. So I wanted to make that clear, just that when you're dealing with non-functions, these other random equations, well, your derivative, now we should expect there to be both variables x and y. And then any information we need, well, if I ask you to find the equation of a tangent line, I can't just give you an x anymore. I'd have to give you an xy pair so that you could plug it in and find the appropriate slope. Right? Let's do that right now. So I know I started with the derivative and then I jumped to these extras, but if we were trying to find the equation of the tangent line to this function at, let's look at the point 2, let's make sure this works, 2 the square root of 12. See, I can't just give you x. If you plug in x is 2, you get y is plus or minus the square root of 12. I'd have to be very clear what is the exact xy pair. You would need the derivative, then you would plug this in to get the slope, then you'd go back to have your xy pair. So like I'm trying to suggest, we'll come back and do all these. I know I'm saying these things very quickly. Just starting to realize that as long as you have dy over dx, it still represents the slope of the tangent line. So we can still talk about equations of tangent lines, and that's how we get the slope. We can still talk about where does the original have horizontal tangent lines, and it's where the derivative equals 0. But this one we're not going to do any more with, because this was kind of lucky. We're going to start seeing the derivative not only involves x's and y's, but solving equations. You know, we might have an x and a y in the same part here, so it's not that easy to always solve the way that was here. So a couple of little points to make, one last one, and then we'll start getting a lot more practice. So let's go back to this original one more time. But now, if I told you to find dx over dy, again, still notation that says find the derivative, but now we're taking the derivative with respect to y. So shortcuts, I mean, we're basically getting the same thing we had up here. Y squared is still a 2y, x cubed is still a 3x squared, but the difference is now here, this does not require anything extra. 2y times dy over dy, so unnecessary. You took a derivative of y with respect to y, take the derivative, use the shortcut, and you're done. But now over here, this is the one that gets tricky. Now you took the derivative, but that derivative is of variable x with respect to y. That will get marked dx over dy. And then I'd still have to finish solving for the derivative notation. So just to point that out, but for all the rest that we're going to do, now I want us to get some real practice. And for the whole next bunch of problems, the directions for all of these is going to be find dy over dx. So let's start with number 1. I do want to point out very quickly here, the book points out some non-functions. They point out a circle, kind of similar to the way I did here, an equation versus the graph, just not a function, but still legitimate to talk about the slope. They then talk about this idea, the curve, the folium of Descartes. It's this special function, x cubed plus y cubed equals something x times y. There's nothing special about that, everybody. It's just another example of something that's not a function. So don't let that bother you at all. I know they do a couple of example problems using that, but it's still just a matter of finding the derivative, recognizing when implicit differentiation does apply. That's the point right here. Okay? So let's find dy dx. Let's look at x cubed minus 4x plus y squared equals 10y plus 1. So find dy dx. So I will take the derivative with respect to x, but everything's ready to go. Nothing fancy, nothing that needs any rewrites or anything like that. Everything is just nice, simple pieces attached by addition, subtraction on both sides of the equation. There's no rewrites, nothing fancy at all. So a straightforward left to right. This is an x, so I get 3x squared, nothing extra. Minus 4x has a derivative minus 4. There's no x left here anymore, but you still took a derivative starting with an x, so once again, nothing extra. Plus derivative of y squared, 2y. That gets the extra marking, dy dx. You took a derivative of y with respect to x, equals, same thing here. It's very quick and easy to say, oh, the derivative is just 10, no extra marking, but it's not about what happens after you take the derivative, it's what happened before. You had a y here, you took a derivative of that y, the y may no longer be a part of the answer, but it still needs to get marked dy dx, plus 1 is plus 0. Now we see something that's a lot more common, right? We're not just getting, well, first off, we did not get dy dx equals. That is absolute garbage, everybody. I need to make that very, very clear. People, they don't understand the marking dy dx. They just see dy dx notation, and they put an extra equals. And now this is complete garbage. You don't have an equation with a left and a right. Now you've got multiple equalities. You've got a string, and this is all just garbage, and it all is because of this. So again, that's the big thing. When does implicit differentiation even apply? It applies when you don't have a function. And we don't have a function. We don't have an f of x equals and a of x equals. We've got this mess of x's and y's. So that's where we knew implicit differentiation was necessary. So the dy dx will come up inside the problem. And now to solve for dy dx, well, you have multiple dy dx's. Group them together. I'm going to algebraically move this from the left side to the right side so that now my left side is just 3x squared minus 4. My right side, well, these are not like terms. They do both have the dy dx, but this is just the number 10. This also has the variable. So I can't actually subtract them. Like this does not equal 8. It does not equal 8y. This is as good as that right side can be. Nothing special about the right either here. It was just easier to move this one term to the right and have all the dy dx's on the right, as opposed to move this one term to the left and move both of these terms to the right. Because either way, if we're going to solve for dy dx, we need all of our dy dx's on one side, and on the other side, no dy dx's. So now on the side with the dy dx, they may not be like terms, but they both have a dy dx, so that could be factored out, and then I could divide this to the other side. So 3x squared minus 4 over 10 minus 2y would be our dy dx. And you know what? While we're right here, let's just jump right in and let's add to this problem. We're going to do this for all problems, but let's just jump right in and add a little more. Let's find the second derivative. Well, first things first, let's remember the notation for higher level derivatives for functions f double prime, g double prime for the second derivative, triple prime for the third derivative. But for Leibniz notation, that would be the second derivative. The second derivative with respect to x. Now the process is pretty much the same. How do you get to f double prime when you start with f? Well, you take the derivative one time, and then you take the derivative a second time. There's no jumping from here to here. You got to get the first derivative to then move to the second. Same thing happens with implicit differentiation. We needed the first derivative before we can get to the second. But here's a quick thing, everybody. Again, nicer aspect of having a function. You went right into the first derivative, and because all this was easy enough, we went right into the second. Because this was already solved for. If you just take another derivative right here, that's product rule. And you have this extra notation you have to deal with. Over here, what's the derivative of 10 dy dx? It's 10 d2y dx2. The derivative of the derivative is the second derivative. But do yourself a favor. If you want the first derivative, well, you have to do this. You can't stop here. You have to finish solving for dy dx. But even if you want the second derivative, still do yourself that favor. Solve for dy dx. I still have to take another derivative. It's not nice, right? I'm going to need quotient rule in order to take that derivative. But now look at the extra advantage. Now think of this like I flip side. So this is on the left side, this is on the right. So when I take the derivative of this side, it's just like what we did here. We went right from f prime to f double prime. The derivative of the first derivative would give me the second derivative. That's the nice advantage. If you solve the first derivative for dy dx, when you move to higher level derivatives, you immediately get that derivative. But now I need my quotient rule. Derivative of the top, 6x minus 0 times plane original bottom, minus derivative of the bottom. Well, that will give me a minus 2, but it's still a y. I still took a derivative of y with respect to x. It still needs to get marked. It doesn't get marked with the second derivative. You only get the second derivative when you take the derivative of the first derivative. This would still get marked with the same dy dx. The same way this did here. It was taking a derivative of a y, got marked dy dx. Well, even though ultimately you're getting the second derivative, in the middle of the problem, that's still just a derivative of a y, it gets marked dy dx. So there's my derivative of the bottom times the original top, all over bottom squared. Notice here, there's no derivative. You did not take a derivative of y here, so don't get an extra dy dx in here. There's a good answer, but there's one last tiny little piece, one last little pain in the butt. We do have this solved for the second derivative. That is a very, very nice thing, and I'm not worried about cleanup. I definitely don't expect you to distribute, FOIL. I mean, if you want to make that a plus, that's certainly fine. But here's the last thing, everybody. You start with an equation that has x's and y's. The first derivative is just down to x's and y's, but now your second derivative has x, has y, and has dy dx. We can do better. And the way we'll do better is simply this. Not worried about any of this stuff. It's just simply, well, I will make that a plus. But right here, the dy over dx. That's the extra bit. We just want variables x and y. So these are all fine, but now this dy dx, I'm going to replace that with what we found dy dx was just a few minutes ago. So again, still little extras. No new derivative rules, just formally using notation. First derivative, we had to solve for dy dx. Second derivative, we're lucky that's already solved for, but don't leave that original dy dx. Get that? That's another good reason to solve for dy dx here. That allows me to get the second derivative isolated right off the bat when I take that next derivative, but also allows me to make a clean substitution. Now, this answer still looks like a big, big mess, and it is. But at least it's just a mess that only contains x's and y's. So, little things, oh wait, can I cancel? No, you cannot. It doesn't factor out of both. Here, those could combine. You could get a common denominator and then do more. But again, that's not necessary. This is good enough. If we really needed this, at least we got it broken down that we can just plug in x's and y's and do whatever little arithmetic along the way. So, okay, a lot from that first problem. We started by just saying find dy dx, but then after we got here, pointed out how we would find the second derivative. So if the problem said find the second derivative right off the bat, all of this was our process. But now, like I said, let's get back and just get some more practice with just plain old finding dy dx. Applying implicit derivatives. So let's call this, so let's find dy over dx. This is number 2. Let's take a look at 4x squared minus 6xy equals the cube root of y to the 4th power plus 7 over x to the 4th power minus tan y. I am throwing a lot at you in this problem. Find dy dx. Okay, we're going to have to take the derivative with respect to x. I realize my notation is going to come up in the middle of the problem. I've got x's and y's, so I don't just get dy dx equals. They're going to come up inside while we're taking the derivative. But before I just jump in, what's my situation? Well, this piece is nice. These pieces are separated by subtraction. That is product rule. X times y. And you can't clean it up in any way. So even though they're different variables, that's still multiplication of variables. That still requires product rule. So maybe you want to make that note. Maybe you want to set up a little u and v. For a situation like this, I like to include the negative as my u. So I'll say that again when we do that. Some people like negative, big set of parentheses, and they do their u prime v plus v prime u, then distribute the negative. I'd rather have the negative inside that derivative the whole time. So that'll be product rule. Here, not too bad, but needs a rewrite. Doesn't matter if it's x or y. We need that to be one exponent, so that'll be y to the 4/3. Here, well, you can be mean to yourself and use quotient rule on this, or you can be nice to yourself and just do a little rewrite. And even though that's a trig function, that trig function still contains variable y. So nothing bad with the derivative, but still having that y, we're going to need the implicit. We're going to need to mark that. So now I'm ready to go left to right. So right off the bat, I get a simple 8x, product rule, uv. Derivative of the first minus 6 times the plain old second, plus derivative of the second. The derivative of y is 1, and then it gets marked dy dx. That's my v prime, all times plain old u. And that's what I was saying, everybody. It's easy to have minus parentheses, this plus this, and you'd have a plain 6, but then that negative would have to be distributed. So I just treated the negative like it was a part of my first function. But now before I move on, still 2 little things to point out. Over here, you took a derivative, but there was no dy dx. So again, it's not every time there's a y, you get a dy dx. It's every time you take a derivative of a y. So right here, Again, especially if you write it out. U is minus 6x, U prime is just minus 6. V is y, V prime is 1 dy dx, or just dy dx if you prefer. So some of us can really need that little bit of extra bookkeeping here, even though the derivatives weren't hard, just to keep track where should that dy dx be. And it's not here. There is a y when I put u prime times v together, but there was no derivative of y here, but over here. There's no y at the end, but that is where we took the derivative of y. That's where it would get marked. Again, that was a 6, and that was a 6 here. Equals. The equals was here, so that's where I'm up to in my derivative, so that's where the equal comes up in the next line. Still just a power rule. 4/3 y to the 1/3, but you took a derivative of a y, gets marked dy dx. Here, minus 28 x to the negative 5. No extra marking. Derivative was a variable x, so nothing extra at the end. Finally, minus tangent becomes minus secant squared y. Some people look at this as chain rule. The derivative of tangent is secant squared. The angle stays the same. Then you do the derivative of the angle. So the derivative of y is 1 dy dx. Other people just, there's a derivative and it contained a y. So they mark it dy dx. Either way, that marking has to come up with this piece. You were taking a derivative of a y here, so it gets the extra dy dx. So what am I going to move? Well, just a tiny little bit of cleanup here. Again, as we always say, do you want to write that as the cube root of y? Do you want to put that x back in the denominator? That's your choice. I'm not worried about that. I'm just worried about you solving for dy over dx. So just here, realize that's a minus 6 dy dx. Over here, nothing too much to be cleaned up. I have 1 dy dx over here, 2 over here. I'm going to leave these alone, bring this to the other side by adding 6 dy dx to both sides. So this will cancel, and now I've got all my dy dx's over here, but this is not good. This is not a dy dx, so get that on the other side. This is just a coincidence, everybody. I know a lot of people have the habit, they just always put dy dx on the left side. That's fine. There's no problem with that at all. There's no problem moving this and this to the left, and then moving both of these to the right, but just certainly trying to take it the easiest path possible. So 1 dy dx move to the right to go with the other two. One non-dy dx term, I'll do a plus 28x to the minus 5 to get the non-dy dx's together. These do not combine, so I've got an 8x, a minus 6y, plus 28 x to the minus 5. Over here, all of them do have the dy dx, so I'm going to factor that dy dx out right now. What's left? The dy dx, the dy dx, the dy dx. If they had anything more in common, that's great. Remember, this is not GCF here. This is all about isolating dy dx. So even if I had, say, a 4, an 8, and a 6, like, oh, they've got a common 2, that doesn't matter. It's the dy dx we care about here. What's left? The 4/3 y to the 1/3 from here, the minus secant squared y from here, and the plus 6 from here. So these three all had the dy dx. That's been pulled out. Divide this to the other side. dy over dx equals this big mess. And of course, at the end, if you'd rather write the dy, realize at the end, 4 equals x, x equals 4, it's all the same thing. So if you just prefer to, at the end, move the dy over dx equals here, but then make sure if you do that, cross all this off. You don't want to have an unequal string. You still want it to be a clear left and right, whether you have the dy dx on the right or on the left. This is your derivative. So I hope that wasn't a terrible derivative. We pointed out several little things here as we took the derivative. We mixed, some product rule, some chain rule. Actually, no real chain rule here. We basically just had a little product rule and some trig functions. Let's do another one. Let's do a slightly harder derivative, and then we'll do a little bit with the tangent line. And like I said, that's really all we want to do here. Just getting used to this derivative. You look into your homework. A lot of it is, again, just the dy over dx. And then the end of the homework, a lot of find the tangent line to the given curve. So, one more dy dx. Let's find dy over dx for the equation. And for number 3, let's set up x cubed y to the 5th minus cosine squared of y plus secant of x cubed minus 1 equals, and on the other side, let's have sine of, let's go xy. More of a mess this time. Still trying to find the derivative, so I'm really just pushing you to apply this new implicit differentiation with a lot of rules going on. So still taking the derivative with respect to x, but looking at my situation. Looking from left to right, multiplication. A little fancier than what we had up here, but that's still multiplication. That needs product rule. Right here, some people like to rewrite this to keep track of where that squared is. And if you didn't see this in the book, we mentioned this but didn't point it out so specifically. There is a massive difference between these two. So again, parentheses count for a lot. If you want to write it in this form, that's why traditionally we put the exponent here so that these parentheses, that we don't need parentheses. This should be clear. The square is on the cosine function. If you want the square on the inner variable, you write it like this. Some people still like to use parentheses to make that clear. Make that explicitly clear that square is on the y, not on the cosine. So both of these would be chain rule, but here it's the outer exponent. That's the outer, cosine is the inner. Here, cosine is the outer, y squared is the inner. So a very, very different situation. And this is the situation we have here. So that's a little chain rule. Here, this is also chain rule, but this is more of this situation. The trig function is the outer and some inner stuff on the inside for the angle. And then last but not least, look at this mess. This is chain rule just like this is, but when you go to do the derivative of the inner, we need product rule. So like I said, this one I really think is quite a handful. There's a lot of stuff to keep track of here. So these little notes, don't go with that problem, just to keep track of. So I'm going to jump right in though. I've set up and realized everything. So now when I go left to right, I know what needs to be done. So right off the bat, using my product rule, derivative of the first, 3x squared, plain old second, y to the 5th. Plus, derivative of the second, 5y to the 4th, gets the extra marking, dy dx, times original first, 3x squared. Next here, chain rule. Start on the outside. Start with the exponent. Minus 2 cosine to the first power. And now the exponent is done. Move to the inside. The derivative of cosine is negative sine. And then just those little things like we said up here, do you just say, okay, that's the derivative and you get the dy dx because you took a derivative of y? Or do you look at that as another step of chain rule? Now this part is done and the derivative of y is 1, but it gets marked dy dx. Either way, we're all on the same page. I'm going to continue my derivative down here, plus. So all of this was the derivative from here. All of this is the derivative from here, plus The derivative of secant is secant tangent. But again, the angle doesn't change. For some of you, maybe you like that chart I made at the end. Secant u has derivative secant u tangent u times the derivative of u. But no y's here, so there's no extra marking, there's no extra dy dx, equals, now take my derivative here, the derivative of sine is cosine, and the xy left alone, times the derivative of what's inside, so times, and now I'm using my product rule, derivative of the first times the second, plus derivative of the second times the first. And now I've got some work to do as far as solving isolating dy dx. Just for space, everybody, I really wanted the challenge here to realize all these little situations. Okay, I threw a lot at you in this one problem to really push your buttons. You're applying implicit differentiation, but even more so, just keeping track, trig functions, chain rule, product rule, a lot of mess here. But solving. No dy dx, this has a dy dx, this has a dy dx, no dy dx. So 4 big pieces on the left side, 2 have dy dx, 2 do not. Over here, you got to distribute this. 1 does not have a dy dx, so this will be y cosine xy plus x cosine xy dy dx. So whichever way here, you're moving a lot. So I'm going to do the more traditional. Leave the dy dx's on the left side, move the others to the left side, the non-dy dx stuff move to the right, and this one will stay on the right. So this is already here. I'm just going to slightly clean it up, everybody. Multiplying these together, 15x squared y to the 4th dy dx. Cleaning this up a tiny bit, plus 2 cosine y sine y dy dx. Subtracting this to the other side, minus x cosine xy dy dx. All of them had the dy dx. So now that could be factored out. So that's my big ugly left side equals what's on the right side. Well, this was already there. It did not have the dy dx. But now this one has to be moved, so I'd subtract that. This had the dy dx. This had the dy dx. This one needs to be moved as well. So that'll also subtract over. Sorry, that's a 5 there. Just make sure that's clear, right? 3x squared y to the 5th. Subtract this over. I'm just going to kick the 3x squared to the front. So this dy dx equals this big mess, and now I finish it up. Divide this to the other side, and for the room I have on my page, really hope you're following, because we literally were going this equals this, but now I'm going to cheat a little bit, dividing this to the other side, so this is on the left by itself, and equals this, all divided by this. Wow, what an ugly, big, clunky answer that is, but that is honestly really as good as we can get it to look. That is as good. Oh, I'm sorry. I just realized, though, I wrote sine. That was a secant. I'm very sorry about that. Secant x cubed minus 1, tangent x cubed minus 1, just to fix that piece. But that's it. I mean, you look at either of these last two, you want to take a second derivative here, that is an absolute nightmare. What a terrible, terrible thing. This one's not quite as bad. So this one I would expect you to be able to do. That would be tough, though. Certainly a lot of work here. This one, no way. Like I said in the first place, I threw so much at you in this problem. There's no way I would ever expect you to take a second derivative for that type of problem. So realize for second derivatives, if I did, it would be something more like this one. Or in the book, they do that as well. They have some more basic examples. So getting a first derivative, not bad, because they're really trying to challenge you to then solve for dy dx, get to the second, and do that substitution. So last thing for today, something we mentioned at the beginning. We have our derivatives. Actually, there's going to be one quick thing I show you after this to try and give us a little heads up for section 2.8. But the last thing that really goes exactly with this section, let's get a reminder of a tangent line. Let's find the equation of the line tangent to, let's look at y squared minus 4x squared y plus 3 equals x cubed minus 1. Let's find the equation of the line tangent to this curve at the point, let's go minus 1 comma, actually I want to make sure this works, everybody. I don't want to give you a bogus point. So if x is minus 1, let's make this a plus 7, so minus 1 comma 8 would be the xy pair. But as we've seen, equation of a tangent line, well, oftentimes we say we have an x, we need an xy. Well, again, I couldn't just give you an x. There would be multiple y's. I want you to have one where that happens. Oh, I'm sorry, minus 1 comma 1. That's what I meant to have, minus 1 comma 1. So that makes sense as an xy pair. If you just plug in x as minus 1, you'd have multiple answers for y. So you need to be clear where on the graph. Without a function, you need both the x and the y. So this equation at this point, xy is given. Well, feels like it's much easier. I only need the slope, but specifically slope here is going to be the derivative, but specifically this derivative at this point. So to take this derivative, well, I need to start by taking the derivative with respect to x. We're back to a more basic one here. Nothing too bad here. I still gave you a little product rule. Not that product rule is the only thing that comes up here. We saw quotient rule when we did a second derivative. We've seen plenty of chain rule as well. But just again, a little more practice. But everything else, very nice and neat, ready to go. Derivative here, 2y, marked dy dx. Right here, product rule, derivative of the first, plain old second, so no dy dx, plus derivative of the second times the first. This is just like what I did before, everybody. I included the negative as a part of my u. Negative 4x squared is what I'm treating as my first to get this direct line. Plus 0 equals derivative here, 3x squared, nothing extra, plus 0. There's my derivative. And you see, it's not always quite so terrible. The dy dx's, yeah, there's two of them, but they're already all on the left, so I don't have to move that. I will move this to the other side. So on my left side, I have 2y minus 4x squared. Both of those had dy dx's, so I could factor that out. So these two just pulled the dy dx out, but that's assuming I move this first. So I added the 8xy to the other side. These don't combine. I mean, little things, everybody. I have 8xy plus 3x squared. You have 3x squared plus 8xy. Same thing. You know, don't let that bother you. Same thing here. I have 2y minus 4x squared. You have minus 4x squared plus 2y. Same thing. Don't let those things bother you. So divide that over. There's your derivative. But again, that's kind of like our generic derivative. It's not a function either, but it's like that. So that's not the slope. You get the slope by plugging not just the x, but the xy pair in. You know, we don't have function notation, but a lot of people try and make this clear that you're plugging values in. So they do this little notation I did here. Here's generic dy over dx. That's just a little bit of notation. I don't mind if you don't use that, but for some people, they like to have it to distinguish the generic derivative versus the derivative with specific values plugged in. Just like the difference between f prime of x, you still have variable x, but f prime of 2, you've plugged the 2 in for x. So here, plugging that in, but I'm going to plug in and do the arithmetic along the way. 8 times -1 times +1 is -8, plus 3 times -1 squared is plus 3. So I'm getting a -5 in the numerator. The denominator, 2 times y, so that's 2 times 1, 2, minus 4 times -1 squared, so -4 times +1. I got -5 over -2, or +5 over 2. Finish, y minus the y equals mx minus the x. And as I always say, no problem you leaving your equation just like that. This one is not terrible at all to solve for y, but that is a very good, fine, final answer. So, the last thing I want to point out, everybody, like I said, this is not technically 2.6. The book doesn't bring this up until 2.8. 2.7, we'll get a little applied section. That'll actually be a very, very nice short section for us. So we'll see that coming up. 2.8 is a pretty tough application section. We'll see a nice little variety of application word problems, and we'll see related, formally we'll call that section related rates, but we'll see implicit differentiation is necessary. So just to give us a tiny warm up there, without even seeing all the application, all the word problem, just to get a basic idea of what's happening here. So let's look at, and let's keep this simple. Let's go back to that original circle that I started with. My graph is not pretty here, but good enough. And let's pretend that we had an object. Maybe it's like a bug or something like that, or maybe this is like a satellite orbit, something like that. So we actually have an object that's traveling along this curve, okay? We can talk about its derivative, but instead of looking at the derivative dy over dx, that's specifically referring to the slope of the tangent line, we could start looking at things like dx over dt or dy over dt. Derivatives that tell us specifically the motion of a variable with respect to time. So that if I'm at this point on the curve and I know dx over dt is, let's do 1, 2, 3. Yeah, this will work. I don't want to go too crazy with scale or anything here, but let's say dx over dt is +1. We'd have to think of that as +1 unit per, and there's some aspect of time here, so let me use seconds here. +1 unit per second. If this guy is moving +1 unit per second, that would be a jump like this. That's his move. But he has to stay on the curve. So in order for him to move that 1 unit to the right, he also had to slide down at that same time. So if this is his derivative of x with respect to time, his derivative with y must have been something negative to indicate that he was going down. Okay? If I was over here at this point and dx dt was +1, well, I'd be moving over 1 unit and I'd still have a negative derivative for y. But if I was up here and I go right 1 unit, now my point jumped up to here, my derivative for y must have increased. So the simple point here, everybody, is that it doesn't have to be a derivative of y with respect to x. You can take a derivative with respect to t. And the point here is that this is telling us something about motion. In this case, how this point is moving on this curve. And if it's going to move some direction with respect to x, it's forced to move some direction with respect to y, or vice versa. So if I know something about this, I can find something about this, or vice versa. If I know how its derivative is changing y with respect to t, then I can figure out how its derivative x is changing with respect to t. You could eventually, if you go into Calc, I don't think this gets brought up, yes, until Calc 3, you could eventually get dy over dx here by using the Leibniz notation and realizing that these would cancel. Treat these as fractions, while dividing by dx over dt would be multiplying in this way, and that these would cancel. The book also did something like this when it introduced chain rule, to show you how, again, this notation, it looks like a fraction, and sometimes we can get away treating it as a fraction. But really, my point was just to realize it makes sense to talk about how things change with respect to time. So a second very, very quick example. If I knew I had a right circular cylinder, aka a soda can, the volume of a soda can is equal to pi r squared times h. But if I know how quickly I'm filling this soda can, or maybe if there's a hole in my soda can and it's leaking, if I know how quickly I'm losing volume, I know how quickly the height of the liquid is dropping in the can. Or vice versa. If I knew how quickly the height is dropping because I have this leak, I could figure out how quickly the volume, the rate at which I'm losing volume as well. And it would all be boiled down to taking the derivative with respect to t. There is no variable t in here. V, R, and h all have very specific meaning in this application, but we can still take the derivative with respect to time. So again, I don't want to get too carried away with that. We're going to say a lot more. 2.8 will be a fairly lengthy section as we try and get through all of this, but it really starts with implicit derivatives.